Welcome to G Fun Facts Online. Today we are diving deep into a landmark achievement that bridges the gap between science fiction and high-energy physics. In early 2024, scientists successfully laser-cooled positronium, an exotic short-lived atom made entirely of antimatter and matter components, for the first time in history. This breakthrough, achieved independently by the AEGS collaboration at CERN and a team at the University of Tokyo, shatters a decades-old technical barrier. By freezing these ghostly atoms, researchers have unlocked a new era of quantum testing. In this episode, we will provide a comprehensive examination of the physics behind laser cooling positronium, the experimental architectures of the AEGS and Tokyo teams, the profound implications for tests of the Einstein Equivalence Principle, and the futuristic potential of developing the world's first gamma-ray laser. Let's start with the paradox of frozen fire. For nearly a century, antimatter has captured the human imagination as the ultimate volatile substance. When antimatter meets matter, they annihilate instantly, releasing pure energy in accordance with Einstein's famous equation. To freeze such a substance seems paradoxical, like trying to hold a flame in a block of ice. Yet, this is exactly what physicists have recently accomplished. The physics community was electrified by the announcement that the AEGS collaboration at CERN and a separate team at the University of Tokyo had successfully cooled positronium atoms using lasers. This was not merely a marginal improvement in temperature, but a fundamental change of state, dropping the temperature of these exotic atoms from a scorching 380 Kelvin, roughly the boiling point of water, to a frigid 170 Kelvin in the CERN experiment, and even further to nearly 1 Kelvin in the Tokyo experiment. This achievement represents the culmination of over 30 years of theoretical work and experimental frustration. To understand why this is so difficult, we must look at the nature of positronium, the lightest atom in the universe. Standard atoms are composed of a heavy nucleus containing protons and neutrons, orbited by light electrons. Positronium, however, is a true exotic atom. It consists of an electron and its antimatter twin, the positron, orbiting each other. There is no nucleus. The two particles have identical mass, but opposite charge, meaning they swirl around a common center of mass located exactly in the middle of the bond. Because it lacks a heavy nucleus, positronium is incredibly light, about 1/1000th the mass of a hydrogen atom. This low mass makes it extremely sensitive to external forces, including the kick of a laser photon, which is both a blessing and a curse for physicists. Furthermore, positronium comes in two varieties determined by the spin of its particles. There is para-positronium, where the spins are opposite. This form is extremely unstable and annihilates into 2 gamma rays in just 125 picoseconds. It is too short-lived to be useful for laser cooling. Then there is orthopositronium, where the spins are parallel. This form is considered long-lived in the quantum world, surviving for roughly 142 nanoseconds in a vacuum before decaying into 3 gamma rays. 142 nanoseconds is the window of opportunity. To put this in perspective, light travels only about 42 meters in this time. In this blink of an eye, the experimentalists must create the positronium, hit it with thousands of laser pulses to cool it, and perform their measurements before the atoms spontaneously vanish into a burst of radiation. The physics of laser cooling here relies on the 1s-2p transition. To cool an atom, you need to interact with its energy levels. For positronium, the handle used by physicists is the transition between the ground state and the first excited state. The energy required to make this jump corresponds to ultraviolet light with a wavelength of approximately 243 nanometers. The challenge lies in the line width of this transition. Because the atom lives for such a short time, its energy levels are fuzzy, a consequence of the Heisenberg uncertainty principle, leading to a broad natural line width. Furthermore, because the atoms are so light, they move incredibly fast at room temperature, around 100 kilometers per second. This speed creates a massive Doppler shift, meaning the laser light, from the atom's perspective, appears to be the wrong color unless it is precisely tuned. Laser cooling works on the principle of momentum transfer. A laser beam is tuned to a frequency slightly below the resonance of the atom. If an atom moves toward the laser, the Doppler effect shifts the light's frequency up, bringing it into resonance. The atom absorbs a photon. Since photons carry momentum, this absorption delivers a tiny kick opposite to the atom's motion, slowing it down. The atom then re-emits the photon in a random direction. Over many cycles, the random emissions average out to 0 momentum change, but the targeted absorptions consistently slow the atom down. For heavy atoms like rubidium or cesium, a single photon's kick is negligible, like throwing a ping-pong ball at a bowling ball. You need millions of cycles to cool them. For positronium, the bowling ball is also a ping-pong ball. The mass is so low that a single UV photon changes the atom's velocity by a significant amount. This high recoil velocity means the atom can quickly be knocked out of resonance with the laser. Additionally, the Doppler broadening is extreme. In a warm cloud of positronium, some atoms move at 10 kilometers per second, others at 50. A standard single-frequency laser is too narrow. It would only cool a tiny fraction of the atoms moving at exactly the right speed and miss the rest. This is why traditional laser cooling, which works so well for normal matter, failed for positronium for decades. Narrow-band lasers saturated the transition too quickly, or couldn't cover the velocity spread. The atoms would either annihilate before they could be cooled, or simply fly through the laser beam unaffected. The solution required rethinking the laser itself, leading to two different philosophies: brute force spectral width by Aegis, and dynamic frequency tracking by Tokyo. The AGIS collaboration, which stands for Antimatter Experiment Gravity Interferometry Spectroscopy, took the broadband approach. They developed a custom alexandrite-based laser system. Unlike standard lasers that emit a sharp spike of frequency, this laser produces a broad pulse of light that covers a wide range of frequencies simultaneously. By having a spectral bandwidth that matches the Doppler width of the moving positronium cloud, roughly 100 GHz, the laser interacts with all the atoms at once, regardless of their speed. In their results, AEGIS demonstrated cooling from 380 Kelvin down to 170 Kelvin. They achieved this without using electric or magnetic fields, which would disturb the antiparticles, a crucial feature for future gravity tests. On the other hand, the University of Tokyo team took a sniper approach, using chirped lasers. They built a system that emits a chirp, a pulse, where the frequency changes rapidly over time, like a slide whistle going from low to high pitch. The strategy here is brilliant. As the positronium atoms slow down, their Doppler shift changes. A fixed-frequency laser would lose them. The chirped laser follows the atoms as they decelerate, keeping the light in resonance with the cooling transition throughout the entire breaking process. This method is more efficient for reaching ultra-cold temperatures. They reported cooling positronium gases to around 1 Kelvin in just 100 nanoseconds. This is effectively stopping the atoms in their tracks. AGIS demonstrated that a large cloud can be cooled effectively in a complex antimatter factory environment, paving the way for bulk antimatter handling, while Tokyo demonstrated the ultimate precision limits, showing that positronium can be brought to a near standstill. To understand the magnitude of this engineering feat, one must look at the facility where it happens: CERN's antimatter factory. Antiprotons are created at high speeds by smashing protons into a target. To study them, they must be slowed down. They pass through the antiproton decelerator and then into the ELENA ring. ELENA is a synchrotron that decelerates antiprotons to just 100 kV, making them catchable by electromagnetic traps. While ELENA provides antiprotons, AEGIS also needs positrons. These come from a radioactive sodium-22 source. The positrons are accumulated in a specialized trap and then dumped onto a nanochanneled silicon target. When positrons hit the silicon, they pick up electrons. They emerge from the silicon not as lone particles, but as neutral positronium atoms, creating the cloud that the lasers then target. Because positronium is neutral, it cannot be held in place by simple electric fields. This is why laser cooling is so vital. It acts as optical molasses to slow the atoms down so they can be studied before they hit the walls. To prove they cooled the atoms, AEGIS used a moire deflectometer. This is a classical gratings-based interferometer. By measuring the shadow pattern the atoms cast on a detector, scientists can calculate their velocity. A blurred shadow means fast atoms, while a sharp shadow means cold, slow atoms. Now, let's look at the holy grail of this research, the positronium Bose-Einstein condensate, or BEC. A BEC is a state of matter formed when bosons are cooled to near absolute zero. Their quantum wave functions overlap, and they lose their individual identity, behaving as a single superatom. Since positronium is a boson, it can theoretically form a BEC. However, unlike normal matter BECs made of rubidium or sodium, a positronium BEC would be a condensate of antimatter-matter hybrids. This brings us to the concept of self-amplified gamma-ray lasers. In a dense positronium BEC, all the atoms are in the same quantum state. When they annihilate, they don't just pop randomly like popcorn. The annihilation of one atom can stimulate the annihilation of its neighbors. This leads to coherent decay. The gamma rays produced would be coherent, moving in phase with each other. This would create a gracer, or gamma-ray laser. Currently, we have lasers for visible light, UV and X-rays. A gamma-ray laser would be orders of magnitude more energetic. The instability of the BEC acts as an amplifier. A spontaneous decay triggers a cascade, resulting in a directed pulse of 511 kV gamma radiation. This device would allow us to see into the nucleus of atoms with unprecedented resolution, potentially revolutionizing nuclear physics and materials science. But beyond futuristic lasers, the primary driver for this research is the missing antimatter problem. The Big Bang should have created equal amounts of matter and antimatter. Today, the universe is almost entirely matter. Where did the antimatter go? One way to probe this is through the Einstein Equivalence Principle. The weak equivalence principle states that gravity acts on all mass and energy equally, regardless of composition. A feather and a hammer fall at the same rate on the moon. Does an antimatter hammer fall at the same rate? General relativity says yes. But if it falls slightly differently, or even falls up, manifesting anti-gravity, it would break the standard model and offer a clue to the missing antimatter mystery. Frozen positronium is the key to measuring this gravitational acceleration for antimatter. Agus uses the moire deflectometer to measure the vertical drop of a beam of horizontal positronium atoms. If they are cold and slow, they spend more time in the gravity field, making the drop measurable. There are other experiments as well, such as GBAR and Alpha-G, which are also racing to test these principles using antihydrogen. The success of laser cooling positronium directly boosts the efficiency of producing cold antihydrogen via charge exchange, benefiting all these experiments. Furthermore, we have Captain symmetry, which stands for charge, parity, and time. This symmetry suggests that a universe made of antimatter should look exactly like ours, just flipped. If positronium's spectral lines differ even by a fraction of a hertz from theoretical predictions, it would indicate a violation of Captain symmetry. Cold atoms mean less Doppler noise, allowing for spectral measurements of unprecedented precision. With the ability to cool positronium to 1 Kelvin, scientists can now perform Ramsey interferometry and other high-precision techniques. This could reveal deviations in the fine structure of the atom that point to new physics forces or particles not currently described by the standard model. The potential applications extend to gamma-ray imaging, where a positronium BEC gamma laser could allow for holographic imaging of nuclear structures or the detection of microfractures in materials at the femtometer scale. There is even speculation about space propulsion, utilizing the high energy density of antimatter annihilation, though this remains centuries away. The successful laser cooling of positronium is more than just a technical milestone. It is the taming of the most volatile substance in existence. For 30 years, the frozen fire of positronium was a theoretical dream. Today, it is an experimental reality. As Agus and the Tokyo team refine their techniques, we stand on the precipice of answering the most fundamental questions of our existence. Does gravity discriminate? Is the symmetry of the universe perfect, or is it flawed? By freezing the ghost, humanity has taken a decisive step toward understanding the substance of the cosmos itself. The age of antimatter quantum mechanics has officially begun. Thank you for listening to this episode of G Fun Facts Online.